If that fails, I'll put this one up on the middle area. Okay. So what was happening in here in this example was we were asked to integrate this linear differential form, and we were asked to integrate it along a certain curve, along this curve C, from the origin to a point with coordinates 1, 1. This was our point 1, 1 in the plane. And we were to go along the curve, which was specified by this equation, y equals x squared. And we did that by taking our linear differential form and using the specification of the curve, translating the whole integral into a much more familiar integral with respect to one variable. And we could do that because of the way the curve is specified. So any coordinate y in our linear differential form can be replaced by x squared, because y is equal to x squared for every point along this curve. And similarly, that this relationship y equals x squared, that induces a relationship amongst the differentials dy and dx, which you can obtain using the chain rule. So simply taking the differential of each side. So we have the differential of y on the left and 2x, the differential of x on the right-hand side. And this then can be used to substitute for the differential dy, which is in part of our linear differential form, and replace it by the quantity 2x dx. So with those substitutions then, we substitute our two-variable linear differential form to become a one-variable one, where everything is phrased in terms of the x variable. We're still integrating along the curve. We're still moving effectively along points on the curve. That has been built in by substituting y equals x squared. So then to finally evaluate it, we just recognize that as we move along the curve from the origin to this point, the x coordinate is varying from 0 up to 1. So we simply integrate between those two limits. And then by the time it gets to this stage, it's just immediately familiar, traditional integral with respect to one variable, and it can be evaluated. So that's where we got to last time. Over the page, we've got some familiar properties, or properties that this new type of integration has. These are properties of path integrals. They are each of them, they're not new properties as such. They correspond either to the very same property that you're used to for one variable integrals, or they're the appropriate generalization of known properties of one variable integrals to these two variable linear differential forms. So this type of integration is still linear. Okay, you're studying linear transformations with Stephen at the moment, so you should recognize what saying integration is linear means. Integration is linear. Well, in the one variable case, it means that if you integrate from a to b, a linear combination of function beta times f1 plus beta times f2, this will be the linear combination of the individual integrals. Okay, that hopefully does not surprise you. That's a known property of integration for functions of a single variable. It's linear, so you can split an integral of a sum is the sum of the integrals, and an integral of a scalar multiple of a function, well, you can bring the scalar outside, factorize it outside of the integral, so to speak. So for our linear differential forms, this becomes the statement that to integrate along a certain curve, say alpha times L1, plus a beta times L2. Now remember, the differential forms have the dx and the dy embedded in them. That says that this is going to be alpha times the integral along C of L1 plus beta times the integral along C of L2. So it behaves in the same way. Integration is still linear. Linear is a nice property to have, okay? Always useful. Or indeed, we might write to dy. If we want, we can separate, we can break down the linear differential form into its kind of x part and its y part. But these functions p and q might still have x's and y's in them. The p is a function p of x and y. Q might be a function q of x and y. You don't get rid of all the x's and y, but you can have one of the integrals being with respect to the differential dx and the other integral being with respect to the differential dy. The second property refers to changing the direction of the curve. So our curves here have a direction to them. They go from this starting point to that ending point. And in the one variable case, you're well used to the property that your integrals go from between 2 points on the x-axis. Now normally in this kind of picture where a is less than b, normally the type of integral that occurs is integral from a to b of f of x dx. Okay, but if the need arises or it occurs in some of our manipulations, this is the same as the negative of the integral from b to a of f of x dx. So you can integrate starting at b and work your way down to a. You still pick up a quantity related to the area underneath the graph, but it carries a minus sign when you integrate against the normal direction on the x-axis. So you have this relationship, and exactly the same thing holds in our current context of our integrals of linear differential forms. For our linear forms, we have that the integral along C of an L is the negative of the integral along C prime of L. So your C might be a curve from this particular start point to that particular end point. Does my red stick out as a different color there? Nah, it just looks the same as black. My blue? No. They both just look like black. The red one kind of looks like, yeah, it kind of looks a little bit different. Oh, looks better then. So the black curve is the curve from here to here. That's the curve C. The curve C prime, red, is starting from here and ending there. So it's the same set of points, but traversed in the opposite direction. Yeah. So the integral of a linear differential form along these two curves will be the same, they'll be the same value, but carry opposite sign. Okay, so the sign gets changed. Sometimes we write, because it kind of fits in with everything else, it makes sense to be allowed to refer to the curve minus C. So if the curve C goes from here to there, the curve minus C goes from there back to here, along the same set of points, but traversed in the opposite direction. Okay, so it's not an abuse of notation. It makes sense to use that notation, so to speak of the negative of a curve. And lastly, our third property that our integrals of linear differential forms has is using intermediate points. So what you're used to from the one variable case, again, you think of this kind of integral a to b But if there was an intermediate point C, you're familiar with the fact that if you are facing this kind of integral, for whatever reason, it might be advantageous or help you in your analysis to consider it as made up of two subintegrals added together. So you can split the range of integration up, the interval of integration for one variable integrals using an intermediate point C. Say that you're integrating over the whole range is the same as integrating first from A to C and adding that to the result of integrating from C to B. That kind of makes sense if you think of area underneath the graph. The total area underneath the graph is obviously the area in this bit added to the area from this bit. Right? Those two sub-areas partition the whole area. They don't overlap, and the two together, the union of them is the whole area. So that's what you're familiar with. The corresponding thing in the current context is to think about our curve, say going from A to B along a certain path, but somewhere along the way there's an intermediate point C. I was using C for the name of the curve, now it's a point, so just be careful. A little bit confusing. But I'll stick with that because oh no, sorry, what did I call it in the notes? Okay, let's stick with the use in the notes. In my notes, I called them C was the endpoint and B the value in the middle. Remember, A, B, and C, they're just letters. You got to think in terms of structurally more what they mean. So here, the idea is the integral from A to C. So sometimes we use this kind of notation of a linear differential form. So the fact that this along the curve is implied. Okay, there's no specific, well, the specific reference to the curve is this two-name symbol. AC from here refers to the curve, the nominated curve from A to C. As opposed, it's not necessarily the straight line. So from the context, we will be talking about this particular curve. So integrating along this curve, the linear differential form L from A to C will be the same as if I first integrated from A to B. Again, it's implied that it's along this curve, and then subsequently integrated from B to C. And add the two results together. Okay, so let's look at an example of utilizing some of these properties. Example 1.15. So what are we asked to do here? Here we're asked to integrate L, which is this form x squared y dx plus 3x plus 2y. In fact, it's the same form that appeared in our original example. This time we're asked to go, so what's the curve this time? The curve is a path made up of two straight line segments, AD and DB, where D is the intermediate point 1, 0. So we're integrating from the origin 0, 0 to the point with coordinates 1, 1. But we're asked to go via this point D, which is 1, 0. And we're asked to go along the two straight line components. So I'll just go hovering above the x-axis, but we're going along this straight line in red, and then up this straight line here. So we're going along the x-axis from the origin to D, and then up from D to this third point, B. So this is our point B up here. So A is the origin down here, and this is our point B. Question? I'm just checking.
No, you're missing a coefficient on the first term. There's a 10 in the example.
10. Oh, fine. Thank you. So in example 1.4, we went along x squared. So 1.14, we use this curve. So here we're going from the same start point to the same end point. We're using a different curve. So we definitely here make use here of the fact that integrating from A to D to B along this curve of L will be equal to first integrating A to D of L and then integrating D to B of L. We're definitely going to make use of that here because we definitely making use of this fact because X and Y behave very differently on AD and DB. On AD is a straight line. It's particularly easy to say what's happening on the straight line. On the straight line, Y is always fixed at 0, and X is proceeding from 0 to 1. So in particular, our differential dy is 0 because Y isn't changing. Y has a fixed value all along AD. And on DB, it's similar but reversed. Here, X is always fixed at the value 1, and Y proceeds from 0 to 1. But as a consequence, then the differential dx is equal to 0 because the x coordinate is always fixed at 1 along the line BD. So this consequence of having constant value for one coordinate and the corresponding differential being 0, that means that the linear differential form simplifies in different ways on the different paths. So it makes sense to split the integral up into the two subintegrals. I can refer to these as subintegrals. Integral only along part of the curve. So the integral along AD of L, this becomes, well, I'm going to lose all reference to y because the differential dy is 0, the y coordinate is 0. So I only have to speak of x, so it's going to be some integral with respect to x. In fact, it's quite easy to do, because if you look at your linear differential form, you can forget all about the second part, because the second part is with reference to the differential dy, and the first part has a factor of y in it, and y is 0. So it's not too taxing to integrate it along AD. On dB, there is something non-trivial happening. So on dB, x is always fixed at 1 and dx is 0. So again, you can ignore this part of the linear differential. Dx is equal to 0. But this part survives because y is changing from 0 to 1. And the x is always fixed at 1. So it becomes the integral from 0 to 1 of 3 plus 2y dy. And that's a familiar one-dimensional integral. You can do that without too much bother. It's 3y plus y squared, evaluated at 0 and 1 for y. So it's what, 4. Yeah. So our original integral, the integral from A along the curve A of L becomes equal to 4. Which, interestingly, is not the same as the value from exercise, or what are these examples? From example 1.14, which was, whatever it was, 5. There we were integrating the same linear differential form between the same endpoints, but along a different path. So it's not surprising that we got a different value. We're moving through different points. And the action of the integral is to sum up the contribution of the linear differential form at all the points along the curve. So the fact we're moving through different points means it's not that surprising. So this is the typical behavior. Most linear differential forms are this behavior is called path independence. So when you've got this property that integrating the linear differential form depends on the particular path chosen between the endpoints, that's called path dependent. Excuse me, misspoke there. Path dependent. So the typical behavior is path dependent. So the integral depends on the path taken. Some linear differential forms are special. Some of them are special properties that makes them path independent. So the form that they have in such a way means that they don't care what curve you use. So path independence would say that, well, if you integrate along this curve, you'll get the same value if you take a very scenic route and come in on some entirely different curve. As long as you go from the same endpoint to the same start point to the same endpoint, it can happen that no matter the choice of curve, the integral will always be the same. But this is very special behavior. We don't know what it is now. We don't even know if there exist such things. But later, with insights from Green's theorem, which is coming at the end, we will appreciate this. Okay, so at the moment it's just a suggestion that somewhere out there are linear differential forms of a particular type, but they don't care what path you choose. They're quite special. There's another example here. I don't think I have much to add to it apart from what's in the notes, so I'll just show it. I've already got that page. Yeah. So in example 1.16, we can see another slightly different way to resolve these integrals. So here you've got a linear differential form here, but here you're asked to go along the semicircular path between 1, 0 and minus 1, 0. So your path of integration here is this circle C. Now before, in our examples up to now, we've evaluated these integrals by converting into one of the two variables. Whereas here we can use a third type of technique, because it's not, if you try and describe this curve purely in terms of only x or only y, and it's maybe slightly awkward because the circle, remember, in Cartesian coordinates, the circle is represented by this equation. X squared plus y squared equals 1. And so if you try and substitute y for x or x for y, you end up with the slightly awkward construction square root of 1 minus x squared, or square root of 1 minus y squared. And you have to split the path up as well, because there's a 2-to-1 relationship. Sorry, that's funny, isn't it? one of the ways is a 2-to-1 relationship, because for any particular y, there's 2 x values that you might have for those 2 points in the circle at a particular height. If we were talking about the whole circle, there'd be also a 2-to-1 relationship between any given x coordinate. There'd be a point in the top of the circle and a point on the bottom of the circle. But we can bypass all of that by effectively moving to polar coordinates. Okay, so we effectively switch to polar coordinates. Effectively switch to polar coordinates r theta. Remember we introduced those? Because this curve is very much more straightforward to describe in terms of polar coordinates. There's a fixed radius. So r is fixed at the value 1. And theta simply proceeds from 0 to pi. Or here, they use t as the angle parameter. So we can parameterize this path effectively by the angle. So when we're talking about parameterizing paths, we often use t for a connection with time. So we think about the path as being made by a moving object starting at time 0 here and reaching its destination at some later time, be it, time equals pi. Have I done the wrong thing? Sorry, the whole thing is supposed to be in this direction, from left to right. Going from -1, 0 to 2, 1, 0. So anyway, upshot of it all, we're going to describe the path differently. So we introduce a third variable, t, this angle or a time-like thing, and t is going to descend from pi to 0. We start at pi and end at 0, and our x and y coordinates are nicely expressed in terms of t, cosine t and sine t. So you can introduce a new variable, specify your y and x in terms of that new variable. That induces, as long as you're using standard functions that you can take the derivatives of, that will induce a corresponding relationship amongst the differentials. So dx is minus sine of t dt, dy is cosine of t dt. So now you've got something to substitute for your x and y's in terms of t. You've got something to substitute for your dx and dy in terms of t. So you can take your original linear differential form and translate it completely into t. And we're going from this point back to this point, so we're starting at t equals pi and ending at t equals 0. Of course, there's no guarantee that this is going to work out particularly nicely for you, but for the values chosen here, it does, because we have this factorization that you can take out this factor cosine squared plus sine squared of t, which of course is equal to 1. Familiar, the magnitude of the radius is the radius of the unit circle. So this becomes an integral of cosine t, which you can then carry out at 0. Okay, there's another little section here, which is an application of line integrals to these little integrals that sometimes used in physics. I mean, you see integrals come up in loads of application areas, but in particular in physics, we have this idea of the work done by a force. The work done by a force as it moves an object through a certain path through a force field. And the work done by the movement there is the force that it's at play multiplied by the displacement. That's the kind of underlying physical principle. In the context of our integrals, how that kind of comes out is things are represented like this. A force is actually a function, a vector value function. So at any particular point in a force field, there's a force at work which moves in a certain direction and has a certain magnitude. Think about the gravity force field around the planet. The strength of it depends on your distance from the planet, and the direction is always towards the midpoint of the planet. In this, if you simplify that the thing is homogeneous, the material is equally distributed across it, then every gravity vector will be pointing back to the center of the planet. Okay, so the force field we're thinking of here is vector valued function f. So it's a vector valued function, so it has components in the x, y, and z direction, and its value is a vector. So its value is a linear combination of I, j, and k. The coefficients are given by these three component functions, fx, fy, and fz. But they themselves are functions. They themselves are functions of x, y, and z. But fx is a function of x, y, and z. Similarly for the others, fy and fz. The position of a body in space is given by its position, again, a linear combination of I, j, and k. And this underlying physical principle of the work done being the force multiplied by the displacement, well, you see the force is changing at every point as you move. So what that translates to is the scalar dot product, the dot product of F and dr. So the vector dr is simply the vector of the differentials, dx, dy, dz. Dx times I, dy times j, and dz times k. So that's one way in which you see these kind of things, these kind of linear differential forms appearing. Okay? So this is one set in 3 dimensions. So our path C would be a path in 3 dimensions. Path in our three dimensions, basically. In this description here. Okay. So I'll be with you again on Wednesday, and then we're going to discuss so-called the other type of integration, which is over the page here, are double integrals. But I'd just like to introduce them a bit more carefully or a bit more gently. So I'm just going to take 10 minutes or so to do that, to do that now at the end of the lesson. So this is section 1.14, double integrals. So, to this particular viewpoint, that the integral of between a and b of a one variable function f of x is the area under the graph of f over the interval from a to b. Well, under in quotes, because if the function is negative, we're talking about the area over the graph, the area between the graph of f. I guess that's a better phrase. Between graph of f and the interval a to b. Okay, you've been looking at that viewpoint for quite a while. So in the two variable case, we'll have our x, y, and z axes. Confusing for the mathographic students because this is a right-handed XYZ system with the Z axis being the vertical axis, which is not the convention we use in mathographics, but this is the more kind of regular mathematical convention. But the picture here is, well, instead of the graph of f, we've got something like the surface defined by f. So this is the surface defined by z equals f of xy. So over any particular point in the base plane, you've got a height. The height of the point on the surface. And the corresponding thing we want to talk about here is we want to talk about, given a general region R, go between A and B now. See, now the domain of the function is the whole two-dimensional xy plane. So in the same way that the interval A to B is part of the whole domain being just the real numbers for the function f of x, the single variable function, for a two-variable function, the domain is the whole of R2. So part of it, a finite part of it, is going to be some kind of nice enough region R like this. And what we're going to talk about is not the area between the graph and the interval AB, but the volume that lies between the surface and this region of plane. You got to think of these vertical lines coming up off the surface, up off the region R in the base plane, that go to the kind of lift of R, onto the surface. Oh my God. Let's make that the vertical. Okay, this picture is far from beautiful, but you get the idea. So a double integral, which is written like this, this gives the volume of space between the surface and R, this region of the plane. R is a region of the xy plane. What we do is we take our region R in the xy plane, and we imagine it's subdivided quite finely. Okay, so by subdividing the x and y axis, we can imagine a quite kind of fine subdivision of the bottom region. So we can imagine R is approximated as the unit. So this is approximating R as a union of little rectangles. Okay, some large number of little rectangles. If we go back to this original picture here, we can imagine splitting the whole volume up into these little rectangular volumes. Okay, so what I've done there is I've drawn one of the little rectangles that subdivide R, Okay, can we keep the chatter down a bit? Thank you. I've drawn one of these little rectangles Ri that subdivide R. I've drawn its projection upwards onto the surface, and we can see the little thin cylindrical part between the surface and the little rectangle Ri that lies in the bottom plane. So the volume line over Ri can be approximated by the area of Ri multiplied by, so this is a, that's not good. He's on. Control. Okay. Shall I switch back? That's weird. It's up on the TV's been like that. Okay, the machinery has defeated me, but maybe not too bad because it's 10 to the hour now. So we'll continue with this on Wednesday. Okay, sorry about that. I've got to finish it like in 1 or 2 minutes there, but we'll continue on Wednesday.
There you go. Cheers.